Oh my God, you guys. I just recorded this whole lecture and it didn't record my screen. So now I have to do it again. So if I sound annoyed, that's why. All right, we're going to talk about kinetic molecular theory and gases. We're going to do a whole chapter on gases in AP, but I do want to do a quick little overview about gas behavior as well as one of the many gas laws that we're going to need. And the reason why I want to talk about this now is because we need to be able to do stoichiometry when we are not at standard temperature and pressure. So you know that mole volume conversion factor that we were using, 1 mole is 22.4 liters? That's only true at 1 atmosphere of pressure and 0 degrees Celsius. Why? I'm glad you asked. That's because gases will change volume depending on temperature and pressure. And why that is has to do with a couple of key things about gases. And so we're going to use something called kinetic molecular theory to describe gas behavior. Here we go. In the late 1800s, two old white dudes, James Maxwell and Ludwig Boltzmann, came up with this theory to describe the behavior of matter in terms of particles in motion. And we know that particles are in motion, whether you're talking about a solid, a liquid, or a gas. Solid particles are vibrating, liquid particles are sliding past one another, and gas particles are expanding to take up the entire volume that they are given. And that's unique about gases. Solids and liquids have do not have variable volume versus gases that do. And so because of that, we've got some special ways to measure and describe and talk about the behavior of gases because of that ability to change volume. So what are those assumptions? First one, we have to understand that molecules of gas have both mass and volume. If you were to throw a balloon on a balance and measure its mass and then blow it up with carbon dioxide, take its mass again, it would have more mass. Because gases have mass. Even though we don't see gases or feel gases, I'm thinking about some fun demos that we would be doing if we were in school together. Even though we don't see them and feel them on a regular basis, gases do in fact have mass and volume. Think about the fact that you blow up that balloon. The balloon is now taking up more space than it was before. The distance between gas molecules is much bigger than the actual size of the molecules themselves. In other words, when we measure the volume of a gas, we're measuring the total amount of space that it takes up, not the volume of the individual atoms or molecules. This is why gases are compressible, right? Because there's a big amount of space or distance between the molecules that if you were to increase the pressure, you can make smaller. Now, we call these assumptions because they're not always totally true. Now, certainly mass and volume is always true. But this idea that the distance between the molecules is very great, of course, that distance can be made smaller with changes in pressure. So again, not always true. When these assumptions are true, we call the gas an ideal gas. We're going to see that definition again when we do the ideal gas law. And if the assumptions are not true under certain conditions, we would call the gas a real gas. So an ideal gas is one that totally obeys these assumptions. The third one is another one that can change depending on conditions. Molecules do not exert attractive or repulsive forces on one another. We assume that the intermolecular attractions of gases are much less than those for solids and liquids. That's why gases can expand and take up the volume that they are given because they're not really attracted to each other. Again, if you push them together, you can change that a little bit. Molecules of gas are in constant random motion. That's why, when I'm burning a candle in my classroom, you can smell it all the way at the end of the science hallway because those molecules of gas are traveling and moving throughout the space. And lastly, when these gas molecules collide, the collisions are mostly elastic. Think about like a bouncy ball. Like when you drop a bouncy ball on the floor, it gets almost all the way back up to your hand. That's what we consider a mostly elastic collision. And we're going to assume that the collision between gas particles are also elastic. Okay, again, so these are the things that describe gas behavior under what we call ideal conditions or under low temperature under high temperature and low pressure conditions, where the particles are really, really spread out and moving quickly enough that they don't have attractions or repulsions between them, and that there's a lot of space between them as well. Okay, so now to talk about the variables that describe a gas. So the things that we were talking about before are sort of statements or descriptions. We can also measure different things about gases. Of course, we're going to measure amounts of a gas in moles. You could also measure the mass of a gas and convert that to moles using molar mass. We're going to measure volume in liters, temperature in Kelvin. Of course, even though we measure in degrees Celsius in the lab, we're going to convert to Kelvin. And pressure has a whole bunch of different units. We haven't talked about pressure before. That's why I listed all of the different units here. Millimeters of mercury, torr, atmospheres, kilopascal, psi, and bar. Chemists use atmospheres, okay? We're going to use atmospheres as our unit. Kilopascals is the SI base unit for pressure, but we're going to use atmospheres. And of course, pressure is just a force exerted over a unit of area. Absolute zero. The reason why we use Kelvin as our unit of measure for a gas is because Kelvin is an absolute scale. It goes from 0 up. It doesn't go below 0. So 0 Kelvin is actually negative 273 degrees Celsius. That's as low as you can go in Celsius. And it's nice to not work with negatives, because when we're talking about gases in terms of particles in motion, you can't really have negative motion, right? So if temperature is a measure of average kinetic energy, 0 should be where all molecular motion stops. And that's what we call absolute zero. Particles are moving slowly. They have low temperature. The faster they're moving, the higher the temperature. And it's convenient for us in these mathematical equations to not have to work with negative values. And instead, we work with our absolute scale, starting with 0 Kelvin. Another vocabulary term I want to clarify for you guys is a vacuum. Often you think of a vacuum as something that sucks stuff up off of your floor. When I say vacuum, I want you guys to think about a place with no molecules of gas, where you have no pressure. So the container on the left has particles of gas in it, which means that they are actually going to hit the sides of the container because of their kinetic energy. And when they do, they're exerting a force over a certain unit of area. There's pressure there. When we're talking about a vacuum, we're talking about a place with no molecules of gas, and thus no pressure. Now, the whole reason we're having this conversation is so that we can do stoichiometric calculations with gases that are not at standard temperature and pressure. And recall that we're using STP as our reference point, and at 1 atmosphere and 0 degrees Celsius, which is standard temperature and pressure, 1 mole of a gas will occupy 22.4 liters of space. But of course, if that temperature or pressure changes, the volume of the gas is going to change as well. So we're going to use STP as our standard. And 0 degrees Celsius, of course, is 273 Kelvin. And that is not room temperature, you guys. Room temperature is usually around 25 degrees Celsius. Now on to our different units of pressure. Like I said, we're going to use atmospheres, even though kilopascals is our SI base unit. So make sure you write down these conversion factors, because we're going to need to be able to convert between atmospheres and kPa, atmospheres and bar, atmospheres and millimeters of mercury, which are also known as torr for torricelli, and atmospheres and psi. If you're wondering where millimeters of mercury comes from, this diagram here on the right is a barometer. Barometers are used to measure atmospheric pressure. So what they are is just like a dish with mercury, mercury being a liquid metal, which of course can flow when air pressure is exerted upon it. So the atmospheric pressure, some days it's high pressure, some days it's low, depending on our weather systems, or rather, well, you could say that the pressure systems determine the weather, or maybe it's like which came first, the chicken or the egg, whether the pressure determines the weather or the weather determines the pressure. Totally up to you on that one. You guys can tell I'm done this lecture 2 times in a row, and I'm starting to get a little bit giddy. The atmospheric pressure pushes down on the mercury, and that mercury will rise up into this container, which of course is vacuumed out up at the top. So however many millimeters that mercury rose that day is the atmospheric pressure that's being exerted on that mercury. So on high pressure days where there's a lot of atmospheric pressure, that mercury will rise farther up in the barometer, and on low pressure days, it will drop back down. And then lastly, our temperature conversion that I already referred to, we're going to measure our temperature in Celsius in the lab and convert to Kelvin so that we don't have any negative values. And so with this understanding of, our general description of how gases behave and how we measure the variables that determine, the pressure, the temperature, the volume, and the amount of a gas, we're going to use those variables, measurements, and ideas of behavior to actually calculate what the volume will be under different temperature and pressure conditions using something called the ideal gas law. I'm sad that we didn't get to do the demos. I guess I could have done them and videotaped them. Maybe I'll just save them and do them in class with you guys this week. And when we get back to school and in AP Chem, we'll do the really fun demos like when I put you guys in trash bags so you can feel the atmospheric pressure. All right, see you in class.